Welcome. This is the Regression Analysis course. My name is Nicola da Serban. I'm an Associate Professor in the Stewart School of Industrial System Engineering. The lecture is Other Regression Methods. In this lesson, I'll introduce another regression approach which deals with correlated data. Particularly, I will focus on correlation in space. This is again the slide on multiple linear regression. In multiple regression, the assumption of independence means that the error terms or the response variable y's are independently drawn from the data generating process. Generally, we only can evaluate whether errors are uncorrelated. What if the assumption of uncorrelated errors does not hold? Violation of this assumption can lead to misleading assessment of the strength of the regression. In the previous lesson, we learned about correlation in time. In this lesson, we'll learn about another classic correlation in data, the correlation in space. Spatial data arise in many fields, including socioeconomics, demographics, surveillance, healthcare, brain imaging, other imaging data, movement data, forestry, environmetrics, among many others. Here are a few examples. In the data analysis example introduced in the previous lecture of this course, one of the predicting variables was the average travel distance to primary care providers for adults, estimated at the community level. We should expect that this healthcare access measure will be similar in neighboring communities, since they have access to a similar pool of primary care providers, and since they will probably have similar access barriers to care. A second example of a special process is a number of emergency department visits per member per month, the response variable in the regression analysis in the previous lecture of this course. While in the analysis I provided in the previous lecture, I ignored the special correlation in the response, we saw that the residuals did show clear correlation, which should be modeled rigorously. A third example is the worldwide locations of outbreaks of a disease or condition, for example, Zika, which has been of a great concern in the past year. In order to accurately predict future outbreak locations, we need again to account for the spatial dependence in the past outbreaks. A fourth example is functional magnetic resonance imaging, or fMRI, used to capture brain activity. A fifth example is a trajectory of the movement of bison in the landscape. Modeling spatial processes requires an understanding of the characteristics of spatial data. Here are a few important considerations. Does the spatial process have a trend? The trend can be a long distance increase or a decrease in the data over space. Periodicity or seasonality is not common for spatial processes. However, we can observe heteroscedasticity, which means the variability varies with space. For example, there may be more variability in urban areas than in rural areas. Another important aspect in the observation of spatial processes is whether the observations are coming from a continuous or a discrete distribution. For example, the healthcare access measure is a continuous spatial process, where the outbreaks for Zika is a point process. Last, spatial processes can be observed over regular grids, such as images. A regular grid is also called a lattice. Spatial processes can also be observed on irregular grids. For example, much of the geographic data are observed irregularly. Communities have different sizes and different shapes. Let's next look at a few examples of spatial processes. Here is the map of the percentage of children in the left map versus adults in the right map enrolled in Medicaid who have had at least one emergency department visit in 2012 in the state of Georgia. The darker the red, the higher the percentages. For the adult population, we see a trend with high percentages in the north of Georgia but lower percentages in the Atlanta area. For children, we identify several high percentages of children utilizing ED spread across the entire state. Thus, we see more of a special trend for adults than for children, but there is higher variability in rural communities than in urban communities in the utilization of the ED for children. This is an example of images using fMRI. The plot shows the brain surfaces showing differences in two parts of the brain in a response of a given task. Performing spatial analysis of the fMRI images, we can highlight areas of activation as shown in yellow in this example. Here is the map of the estimated smooth probability for the trajectory of bison in the landscape, highlighted in red, characterizing the movement of bison. This estimated trajectory can be used to identify preferred trajectories when the bison moved between foraging areas. It can also be used to assess mode and habitat features, providing valuable information on landscape connectivity. This slide provides a snapshot of the basic modeling of spatial processes. For the simplest spatial data analysis, the response data are YS, the space-varying observations, the space-varying responses, where S is the index for space. For example, S could index communities in geographic data or voxels in imaging data. We generally use different modeling approach if YS is a continuous spatial process as opposed to a point process. Two assumptions in modeling spatial processes are stationarity, meaning that the probability distribution of the spatial process does not change when shifted in space, and isotropy, meaning that the distribution of YS is the same in all orientations. Much of the spatial advanced statistical modeling focuses on how to relax such assumptions, which are very restrictive for spatial processes. Last, it's also important to identify whether the spatial dependence is more localized or so-called small-scale dependence in comparison to strong dependence over large distances. All these aspects are important considerations in modeling spatial data. The field of spatial statistics, just like time series analysis, requires an entire course for covering modeling approaches for spatial data. In summary, in this lesson, I introduced yet another regression analysis approach that generally deals with correlated data, but the correlation is in space. Thank you.